In this video, we'll talk about how pores can get filled in imbibition, and we'll show that if it were just pore filling, there'd be no trapping. But with snap-off, there's a huge amount. So, of course, reality is somewhere in between. But let's just go through this and we'll do my schematic pore and throat and see what I mean. So imagine a sort of case like this. Here's a pore, and I've got 3 throats. And in the previous video, we talked about snap-off. So you fill the throats in order of size, and let's, for the sake of argument, say this was the smallest. So then there's a meniscus here. This was the next smallest. There's a meniscus here, and this was the next smallest. Okay, so now we've got these 3 throats filled with water. And you might say, well, I know what's going to happen next. You fill this throat, and then we trap the non-wetting phase in the centre of the pore space. That's a possibility. But we've also shown that capillary pressure for snap-off can be very close to 0. It's not very favourable. Why? There's no factor of 2 because it's layer flow. There's actually, if anything, a negative curvature in the other direction. And then there's this tan theta, tan alpha term, okay, that again is taking stuff away. So maybe there's something else. Well, there is. As the capillary pressure decreases, you can imagine, remember there's water in the corners in the pores, that we begin to move out like, well, hang on, what's stopping us doing this? We can have a piston-like advance, and now I'm going to define exactly what I mean like that. So what's stopping us doing this and just moving up through the pore space? So piston-like advance is not like swelling a layer. Swelling a layer is you move along a layer and then you move out that way and you've got one curvature. Piston-like advance is like a piston. You've got curvature in 2 directions. So here it's curved like this, but in the other direction it's also curved. This is 3-dimensional. So this piston-like advance, well, roughly speaking, the capillary pressure for this, PC, is 2 sigma, right? In piston-like advance, there's curvature in both directions. So it's 2 sigma, roughly speaking, cos theta. Yes, it's the advancing angle, but that's true of snap-off as well. And we've divided by the inscribed radius of the pore. Now, let's think about this carefully. This is versus PC for snap-off, SO, is 1 sigma cos theta 1 minus tan theta tan alpha over RT. And it's the highest capillary pressure process that happens first. You start with a high capillary pressure and go down. It's the highest capillary pressure. So snap-off should win because the throats are small. Divide by a small number, you get a big number. Disfavoured in pores because they're bigger. On the other hand, there's no 2, there's this term, and there's also the effect of the other curvature. So what wins? Depends. We have very big pores and very little throats. Snap-off wins lots of trapping. If the pores and throats are a similar size, there's much less, because just as you're about to trap, aha, I've trapped you, non-wetting phase, this piston-like advance comes to your aid. But this was assuming that all of the surrounding throats, bar 1, were filled with the wetting phase. If all of the surrounding throats are filled with the wetting phase, by the way, it's trapped, game over. So we call this process I1. I for imbibition, obviously. 1 means there is 1 remaining throat that was not filled. Okay, so you might say, well, that's fine, but it does rely on all of those being filled. So what happens if we have an I2 event? So an I2 event would look like this. And let's draw this out. So imagine these two throats get filled. Okay. Now it's more difficult, because if I consider the radius of curvature needed, I'm not filling from all directions, I'm only filling from two. And in fact now, you can see that it's quite difficult to advance, and you get quite a large radius of curvature here. So if you go through the geometry, and this is not very well drawn, right? You have remember this is wetting phase, you have to have a contact angle that's less than 90 degrees imposed. You see that here, just to get through, sweep through the pore space is quite unfavourable. We've actually got quite a large radius of curvature. And that just comes from the geometry. I agree my diagrams aren't fantastic, but it really is as simple as draw it out. If you draw this out, you can normally get something that looks sort of like a circle in the pore space controlled by the inscribed radius. When you start getting to I2 processes, it becomes much more complex because it's the largest radius. Not here, where you've got quite a small radius of curvature, it's the largest radius of curvature that's going to control the displacement. So here, for I2, PC is much lower. There's a much larger radius of curvature. And then the final one, if we've got three throats, if there's no throat at all, you can't fill. So the final one is going to be what's called the I3 process. Okay, so I can draw it down here. Here, the water advances from just one throat. And if it does that, you can actually have to have a situation where the water bulges out into the oil. And you might say, no, that's not right. Yes, it is. This is the contact angle. It's less than 90 degrees. Okay? So this is a contact angle of, say, 30 or 40 degrees, perfectly reasonable. Then it gets easier, then it gets flat, but then it has to bulge out again to get across the throats. So here, the capillary pressure can actually even go negative. So PC is negative. So what this means in terms of pore filling is, as a rough approximation, does depend exactly on the geometry. You have to look at all the details, but now with three-dimensional imaging, we can look at what's happening. If you've got all the throats surrounding a pore, bar one, roughly speaking, you've got this 2 sigma cos theta over RP. If it's an I2 process, the capillary pressure is lower. It's still positive, so it still happens at a positive capillary pressure, so that's still favoured, but much less favoured. And I3, if you've just got one and you just want to keep sweeping up, is extremely disfavoured. Normally happens at a capillary pressure around 0, or indeed even a negative capillary pressure. Now, what does this all mean in terms of real systems? There is, in fact, a very subtle competition between essentially I1 events that do not lead to trapping, because that's the most favoured. Just as you're about to trap is just when it's most favoured. And snap-off that leads to trapping. And furthermore, when we're comparing the radius of the pore and the radius of the throat, this is, by definition, the widest throat. So it's snap-off in the widest throat versus the I1 event. I2 and I3 are much less favoured, so much less common. So actually the degree of trapping is a balance between these two events, and that is determined by pore and throat radii, how angular, how rough the surface is, and the contact angle. And in the end, that's something that we just have to measure. We can model it, but with a simplified diagrams like this, it's very difficult to be more quantitative. But there is actually one other interesting consequence. if I had this piece of rock, it's dry. If I inject water into this rock, actually, if it's dry, it's quite likely that I trap virtually no water, virtually no air at all. Whereas if it were wetted first, and then we injected, say, air, and now water came again, and there were wetting layers, we get a lot of trapping. And the reason is because if it's dry, we can't have snap-off because we don't have wetting layers. So I'm going to illustrate that, what that means in terms of macroscopic displacement, next. Okay, so let's go back to our normal schematic porous medium. This. And we're going to consider a case where we have either a completely dry porous medium, so it's actually primary imbibition, so it's the wetting phase moving in for the first time, or indeed a porous medium where, for whatever reason, smooth surfaces or complex wettability state, we actually don't have wetting layers. So we're not allowed to have the water creeping through the pore space in wetting layers. So what happens there? Well, we get what we're going to call cooperative pore filling. And by cooperative, I mean that the pore filling is aided if it can cooperate with neighbouring throats. So with one throat, it's difficult. If I've got a friendly throat next to me, it's easier. And with three throats, it's much more easy. So what happens? Well, of course, I fill all the throats, and this is by piston-like advance. Actually, it's a 2 sigma here, because this is the inlet. I can push the water in. But if there's no wetting layer flow, unfortunately, we're immediately hit with difficulty. We're going to have an I3 event. So we're going to have a capillary pressure that immediately is close to 0. But as soon as we do this, we fill the pore, and this will be the smallest pore. Probably the smallest pore is the easiest to fill with a wetting phase that likes the small regions. And then we fill the neighbouring throats, and this is by piston-like advance. Okay, what happens next? Well, okay, we can have an I3 event here, which I just said is very unfavourable. An I3 event here that's very unfavourable. Just a moment. This is an I2, cooperative pore filling. It's easier to do I2 than I1. So, sorry, I3. This was an I3 event. This is an I2 event, which happens more favourably than any I3 event. So what happens here is, well, it fills here, then it always fills the throats. It fills here. Now, if this were, if I had time and you weren't so bored, okay, we could keep going, right? Right? If this was an array going up, we'd still be filling with a cascade of I2 events. And then what happens next is we fill this line, then we see the smallest pore, which maybe is this one in this particular case, so this is my I3. But once I've done this, suddenly, we can do all the I2 events, and we get a cascade down like this. So just a moment. If we do this, we have one unfavourable step. We have to do it. There's no way around it. Snap-off isn't going to help us out. And then we get a cascade of I2. And then we do it again. And then we do it again. Well, what results here is what's called flat frontal advance. There's no trapping. Now, that's almost the opposite, as I said. If we're dominated by snap-off, we get a lot of trapping. The non-wetting phase is trapped in the widest pore spaces. So even if they're numerically not that many, they're the widest bits with the most volume. If on the other hand, there's no layer flow, then there is little or no trapping. And this is true. You might say, well, that's just because it's very regular geometry. But imagine, in general, we have some sort of wetting front like this through the pore space. what's the easiest event? To keep moving like this, or to keep moving around and surround an area? This is going to require, you've got a throat here, but this is going to require an I3 event, or depends how many throats there are, but there's only one connected throat. On the other hand, here, you might say, oh, we're about to fill in and get trapped. But here, this pore here, if we sort of zoom in, is surrounded by all but one throat. So it's most likely to fill here, least likely to fill here. So even if you have a wide range of pore size and a rather irregular topology, yeah, okay, lots of other things are going on, the tendency is, without layer flow, to have very little trapping. It's not that it's impossible, because you could always have some anomalously small regions of the pore space here that get filled and surround that pore. It's not impossible, but you get much, much less trapping. So cooperative pore filling on its own gives you flat frontal advance and no trapping. Snap off on its own gives you a huge amount of trapping. So we'll finish this video by summing things up in terms of capillary pressure. So here's my capillary pressure. Here's my saturation, and we watch as phase 1. This is 0. This is 1. Now let's draw primary drainage to begin with. It goes this way, by the way. Okay. This, say, is the entry pressure. Okay. Now we have an imbibition process, and I'm going to draw the function first. So this is secondary imbibition, and this one is primary. By the way, the number with the little o means array, right? And it's just in this case, it's a time sequence: primary and then secondary. Okay. So what we notice here is the secondary imbibition capillary pressure lies below the drainage capillary pressure. Why? Well, we know the reasons why. This is called capillary pressure hysteresis. So capillary pressure hysteresis is like contact angle hysteresis. You go one way and then you go the other way and you see something different. And there are 3 reasons for capillary pressure hysteresis. The one is contact angle hysteresis. Right, and there are 3 reasons for that. Right, but let's not... if you remember, the contact angle theta A is greater than theta R. So if we have a capillary pressure, and the classic is 2 sigma cos theta over R, even if we're looking at the same element with the same type of displacement, theta A is larger, which means the cosine is lower. So when it's advancing, it's lower than when it's receding. So contact angle hysteresis, we haven't described it explicitly here, but yes. The second, which we have explicitly talked about, is its different displacement processes. Now, what do I mean by that? Well, in primary drainage, it's piston-like. It's always 2 sigma cos theta over R, or a close approximation to that. There's always the 2. When we have imbibition, if there's snap-off, you fill the same throat, so a given throat, label that throat, hello throat, okay? In drainage, it filled with a capillary pressure of 2 sigma cos theta over R. If it fills in snap-off, it's the 1 sigma over R, and then the other bunch of terms. So it's a different displacement process, which always has a lower capillary pressure. And the third one is you don't get back to 1 because you've got trapping. So typically, the capillary pressure for the same saturation, okay, if we look at the same saturation here, may be a half or a third of drainage. Right? It's typically much lower than dredge, not a little effect, a few percent, right? We got factors of 2, we got geometric factors. It's a big difference. Then the degree of trapping. The amount that is trapped here, that's trapped phase 2. So this distance is S2 and R for residual. It's a trapped saturation. Now, if we had just snap-off, the trapped saturation would be, almost 100%, right? Because every single pore would be trapped. If we had no layer flow, if we had no snap-off, very little is trapped. But if we consider most of the porous media we're concerned with are these sort of granular porous media, soils, rocks, there is genuine snap-off and there is some degree, in fact, often a significant degree of cooperative pore filling. And so typical values of this residual saturation, if we have a wetting phase, if this remains a wetting phase throughout the imbibition process, then this value is typically in the range of about 0.2 and can be as high as 0.5 in, say, gas-water systems, which remain very strongly water-wet, can be as high as 50%. But normally that's the typical range of residual saturation. Somewhere between 20 and 50% of the pore space remains trapped, and that's due to snap-off.